Good afternoon, ladies and gentlemen. It's precisely 12:30, so welcome to this free-for-all webinar. I have an awful lot to get through today, so I'm not entirely sure that I will have the opportunity to answer any questions, but I will have a look at the end. So my name's David Brown. I guess a number of people would know me, and I'm going to spend the next hour talking to you about what's coming your way in 2028. And I am only going to give you a flavor. There is so much coming your way, and I appreciate that many people have a wider scope than just my rather limited steel world. But the Generation 2 Eurocodes are going to affect people, and they're going to affect people very, very significantly. So this webinar for the SCI, at least, is just the start. There will be, I'm sure, courses in great detail as the months crank on towards 2028. So I'm going to turn my video off so we can focus on the slides. So there we go, and I'll turn my video on right at the very end. So these are the things that I'm going to cover, and I would again say that I'm just giving you a flavor. I'm not diving into things in great detail or explaining things. So I will look at EN 1990, I'll look at the parts of EN 1991 that I'm aware of and know something about. Of course, I'm going to focus on EN 1993, where we know quite a lot, and I'll be interested in 1993, 11, 18, 110. The big date down at the bottom is March 2028. Many of these Eurocodes are now published, so people are ringing up the SCI and they're asking us for advice on particular clauses. You shouldn't really be using the Generation 2 Eurocodes yet. They're not a consistent set. You haven't got the national annexes, but that doesn't seem to be putting people off actually opening them up, having a look, and in some cases trying to use them. I would commend you to open them up and have a look, and you will see the size of the challenge which is facing you. In 2028 then, will people be using the Generation 2 Eurocodes? Will we change on one day from using Gen 1 to Gen 2? Well, probably not. Lots of people, certainly in the United Kingdom, remember we are governed by the building regulations. Although the building regulations currently cite the Generation 1 Eurocodes, there's no obligation to use them. So many people in the United Kingdom are still using BS 5950 and still using BS 449. The building regulations, well, they will need to be changed if they're going to cite the Generation 2 Eurocodes. And there are some questions about that, I think. So it's not entirely sure that they will be mentioned in the building regulations as of March 2028. I want to emphasize, ladies and gentlemen, that this is a huge issue. It is a huge challenge. So many things are changing that will have a very broad impact. So in my rather limited world of the steel world, design resources, they will change. The references will change, the clauses will change, the values that you calculate will change, the procedures that you follow will change. And that means that everybody who prepares software, the software will have to be changed. And that won't be just the analysis and design of members. That will be lots of ancillary software. So the people who provide software to enable you to select a cold rolled purlin or a side rail or something like that. Many people use software to design composite beams. Well, that will all need some modification as well. So very much today is the start of a campaign, and you could imagine as we get nearer and nearer 2028, there will be a whole range of very detailed courses which the SCI will provide. So where are we 2 years in advance? Most of the Eurocode parts are complete, and very many have been published. Almost incredibly, there are now starting to be some early amendments. So even though in general the national annexes are not complete and not published, there are already some early amendments. The major work, if you like, of completing the Eurocodes themselves is done, I would say. and now the focus is on the national annexes. So lots of people are very busy preparing the national annexes. Some have gone for public comment, you might have seen those. Some are going for public comment, and I would expect a whole flurry of them later in the year. If we take a step back, these were the general Gen 2 ambitions. You can read those, make them easier to use, improve clarity, reduce the nationally determined parameters. So perhaps all those things have been achieved. I'm a little bit cynical. I'm not so sure. Because to make them shorter, I think what's happened is that some of the content has been put in annexes. So the core Eurocode might have less pages, but overall, the page count might have, in fact, risen. I think many of the changes, and I will show some of these later on, are driven by academics who have spent quite a lot of time looking in detail at the application of the code clauses, and perhaps they've identified where something could be improved a little bit, or perhaps where something could be made safe a little bit if they perhaps thought it was a little bit unconservative. So lots of people have been doing lots of research, and that means perhaps that the clauses are driven by that research. They're perhaps not as pragmatic or as simple and as conservative as our history of code writing here in the United Kingdom. Lots and lots of people have been doing very many finite element analyses, looking at the results from those, and then some of the clauses you'll see are clearly curve fitting to the results. I'll show you some examples of that later on. We've got crazy formulas with indices or powers to 3 decimal places. It's difficult to see the mechanical background to that. Clearly they have been developed because of lots and lots of finite element analyses. Here is my first example. So on this particular slide, you can see things, if I get hold of the right pointer, here we go. You can see things to the power of 2 and a ratio there to the power of 4. Clearly there is difficulty in explaining any mechanical background to a ratio which is to the power of 4. This is curve fitting. And if you look at some of the precision down here, the numerator 91.78 and the denominator to a power of 0.892. So lots of precision, and that will be driven by finite element analyses. So the code clauses that I know and love, for example, 661 and 662 and 610 and 610A and 610B, well, I'll have to revise my little brain cells because they will all be renumbered. Generally, there are fewer nationally determined parameters, so maybe that's good. Some of the content that we are familiar with has been lost. One particular thing for us in the United Kingdom is that we analyze our portal frames plastically, and therefore we want to consider the stable lengths next to a plastic hinge. Well, it was decided that really that was a UK-centric interest, so that has been lost. Don't worry, ladies and gentlemen, because it will appear in due course in a revised SCI publication, because that sort of guidance is essential for us in the UK. I thought I'd give you a little flavour of some of the other things that appeal to me as I've been looking through the codes. We've now got the opportunity to allow for climate change. The challenge would be, well, what amplifier do you actually use to allow for climate change? The jury's out. Are things getting worse? Are things getting more extreme or not? Is that same trend seen in all climatic actions? So, for example, in the United Kingdom, are we going to have more extreme snow, or with climate warming, are we going to get less extreme snow? It's not easy to call. I was interested to see that 1991-14, so that's the wind code, has got wind on cooling towers. In my experience in the United Kingdom, we've been getting rid of cooling towers, so to add that in seems a rather strange sort of feature. And finally, one uniquely to the steel world, the additional resistance that we can get by a clever trick with semi-compact sections, and I'll show you that a little bit later on. So here is 1990. this would be where we would get our combination of design actions from. So some modest changes. Thankfully, I'm not involved with geotechnical design because there's an awful lot of additional information in 1990 relating to geotechnics. So for people doing foundations, that will be a key Eurocode for you. The expressions that I'm generally interested in, of course, are to develop the design combinations of actions. So I would know those as 610, or the option of 610A and 610B, and you get a slightly better answer at lower load out of the combination of 610A and 610B. Well, those numbers have been changed, so now it's 812, and then the most onerous of two expressions in 813. So it isn't 813A and 813B anymore. It's two expressions, but they're all within 813. And to me, that's become really silly because over here on the right-hand side, when you refer to either one of those expressions or the other one, instead of referring to them as 813A and 813B, crazy, in my humble opinion, they refer to the upper part of 813 and the lower part of 813. Maybe those are the rules, but to me, 813A and 813B would have been the way to go. As you look at the formulas, you will probably recognize that they're exactly the same as 610A and 610B, and the top one is exactly the same as 610, so no change there. And the values that we will use, well, there is no United Kingdom national annex yet, but I would expect that we will take the recommended values. So the values that we are familiar with, 1.35, 1.5, and 0.85. There is a table of the psi values. So in the combinations, we use psi 0, psi 1, and psi 2. Those remain a nationally determined parameter, and there is no national annex yet to EN 1990, so I can't comment on those. We made one or two changes in the current national annex, and therefore I would expect one or two changes in the Generation 2 national annex. So I've moved on to 1991. So we would get imposed loads on floors and on roofs from 1991-11. Another thing that we used to get from EN 1991-11 was the impact loads on car park structures. Sadly, that's no longer in 1991-11. That should have been moved into 1991-17, which is all about accidental actions, you'll recall. Sadly, it's not there either. The UK used that annex extensively, and therefore the national annex to 1991-17 is going to import what we would have known as Annex B in the current version of 1991-11. So that would be the familiar impacts on, for example, columns in car parks. The UK National Annex is likely to have lots and lots of subdivisions for imposed floor loads, just as it does now. So we await the publication of that National Annex. There is a general observation that the appropriate floor load for a general office should be a total of 3 kilonewtons a square metre. That would include an allowance for movable partitions. So whichever way you cut it, the total should be about 3 is the recommendation. I'm not sure whether people will observe that recommendation. I suspect that many people will still adopt 5 kilonewtons a square metre, and they will continue to add 1 kilonewton a square metre for movable partitions. And all I would say is that that's very conservative, it's very expensive in terms of pound notes, and it's very expensive in carbon if we still continue to adopt that very conservative value of 5+1. Maybe we should all be braver and adopt 3 as our grand total. Roofs are important for us in the steel world. I'm thinking about single-story buildings. The Eurocode still says 0.4 as a distributed load on a roof. The UK National Annex will say, I believe, 0.6 just as it does now. The concentrated load is going up a little bit. There is a feeling that people are getting heavier based on some real data, that people are generally getting healthier. The good thing, I think, is that the UK National Annex at one point was considering increasing the roof load to 0.8 kilonewtons a square metre if the roof slope was less than 5 degrees. So probably good news for flat roofs, at least, that remains as 0.6 kilonewtons per square metre. This is the wind code 1991-14, which has not been published yet, so I only have access to a preliminary version. What I've done on this slide is I've looked at the PDF of that preliminary version. I've made each page very small because this particular version is coloured yellow where there is a change. And that's just to give you an idea of the amount of change in 1991-14. It is very considerable in the core Eurocode. And those of you who know 1991-14, you will know that the UK National Annex is a very substantial document and makes significant changes. I would expect that to be exactly the same with 1991-14 Gen 2. So this slide is saying that the core Eurocode is changing quite a lot. I still expect the UK National Annex to have even further changes. I'm unable at this point to say anything more about the wind code. I can say a few more things about the snow code. So there is some drama here. We are used to a uniform snow case, and then we are used to a whole range of accidental cases. So snow in a valley, snow behind a parapet, snow blowing off a tall roof onto a lower roof. And in those accidental situations, well, we take the partial factor as 1.0. In future, there will be no accidental actions due to snow. So the valley condition and the snow behind a parapet and the snow blown off a high roof onto a lower roof, they will all be persistent cases, and they will attract the partial factors, for example, for an imposed action of 1.5. I should have said a variable action of 1.5. So quite significant changes in this area. You would immediately think that that will be a very onerous penalty if the valley condition and the parapet condition become a persistent load case. Well, they are relatively onerous, but the coefficients which define the depth of the drift, for example, they are all reducing. So maybe it's not as bad as you first think, but it will be quite a significant change, and I think many people will say that the overall load will be increasing. So you kind of lose a bit on applying the 1.5 factor, and you gain a bit because the coefficients are perhaps not as severe as they are currently. So the top of this slide is what we normally do. We have a uniform case, which is a persistent case and attracts the partial factor for variable actions of 1.5. And then entirely separately, we have accidental cases of snow in the valley or snow behind a parapet, and we use a partial factor of 1.0 because it's an accidental case. Well, in 2028, it will not be like that. You will also notice in the drifted cases, which are now called redistributed cases, that the redistributed snow is additional to the uniform snow. Okay, so perhaps on the right-hand side here, what we might have imagined is a drift that's redistributed and is additional to the uniform snow, and the same thing here in the valley case. So probably we might be a little gloomy about those changes. They will certainly have an impact on steelwork, and they might well have an impact on secondary steelwork. The only bright note on the horizon is that the value of the summation, if you like, of the uniform snow and the redistributed snow in this location or in the middle of the valley is generally less than the accidental case that we're previously aware of. So maybe it won't have such an impact on the secondary steelwork, but I believe it will have an impact on the primary steelwork. We need to be careful with that. This is a portal frame. We are very used to a uniform snow case entirely across the top, but there is a redistributed case. There always has been a redistributed case where we remove all the snow from one roof slope. Many people in the UK strangely don't seem to verify that case, but they should do. It's in the current Eurocode. We should be removing all the snow off one particular slope. In the 2028 version, notice that there is in fact no snow on one roof slope, and there is slightly more snow on the remaining slope. So some of the snow gets blown off, and some of the snow which is blown gets redistributed onto, as drawn, the right-hand slope there. Now, at a portal frame slope of 6 degrees, you'd probably hardly notice the difference. The increase is very small. But for other forms of structure, then that additional snow on the one roof slope, could be quite significant. 20% extra wind-blown snow at roof slopes of 30 degrees. So something to take care of. So that was a bit of a trawl through 1990 and 1991, the interesting bits. Anyway, we're moving on to the Steel Code 1993. There are 2 new parts, beams with large web openings. So fortunately, that generally follows previous guidance that the SCI has published. There are some modest changes, so software will have to change and design routines will have to change. And a brand new part, part 14, design assisted by FE analysis. So loads of people are using FE these days. So it's probably right that there is some guidance available, and there it is in part 14. Gen 1, 96 pages. Gen 2 is 120 pages. So, well, it's become larger rather than smaller. It is published. It's been published for some time. We expect an early amendment. I don't believe the early amendment has yet been published, but we expect it, and we're looking forward to changes in the buckling of angles. This is a summary of what's been lost. If it's got a line through it on the left-hand side, those things have been lost. Annex A, probably in the United Kingdom, we didn't use it very much, so that's perhaps okay. Sadly, the stable lengths next to hinges in Annex BB, that, as I said previously, is lost, but that will be resurrected in an SCI publication. The new thing, which I'll talk about a little bit later on, would be Annex B, semi-compact sections, and Annex E. So they are statistics of manufacturing. So out of a whole range of tested values, what sort of production do we get from across the European Union? And they are presented in Annex E. And if you're very good, you would be able to calibrate your partial factors against those steel strength statistics. So that might be useful for researchers in particular. Whole range of well, different types of analysis now in 1993-1-1. They have always been there, but they perhaps haven't been developed as much as they are in Generation 2. So if members are really chunky and therefore imperfections don't have any significant impact, and if frames are really stiff and second order effects in frames don't have any second order impact, well, we don't then have to worry about imperfections, and we don't have to worry about second order effects. It seems a bit stupid to say that, but that's the truth. If we did have something where we didn't need to worry about imperfections and didn't need to worry about second order effects, I think it would be an entirely unrealistic solution. It would be very, very large members for the sorts of loads that we're trying to carry. Frame stability is one of my favorite subjects. So over on the right-hand side, this is the current expression that we use. Over on the left-hand side for sway stability, well, it looks to be a different expression, doesn't it? But actually it's not, because this KST, which presumably stands for story, is the force over the deflection And if we substitute, therefore, the things that we know and do a bit of rearrangement, well, actually, we come back to exactly the same presentation that we had before, except we've got different names of variables. So we've got a horizontal force and we've got a movement due to the horizontal force. We've got the height of a story and we've got the summation of the vertical loads. So that's exactly the same as over on the right-hand side, but presented in a different fashion. These are the different analysis methods. It's presented as a flow chart, so it's not really telling you what to do. I think it's really should be perceived as saying, well, what you can do. It will take some explaining for sure, because up at the top here, method M0, everything is so chunky that we really don't worry about imperfections, and we don't have to worry about second order effects. Somewhere in the middle, well, that's where we are now. Yes, we have to concern ourselves with imperfections, and yes, we have to allow for second order effects in our analyses. And somewhere down at the bottom is if we allow for absolutely everything in the analysis, so we allow for imperfections, we allow for second order effects, well then all we need to do after that is check the cross section. So that will be the one extreme. Members are so chunky and so stiff that we don't need to worry about second order effects and imperfections. And at the other end of the extreme, we would allow for everything within the analysis, and then all we need to do is a cross-sectional check. So probably I suspect that we will remain generally where we are normally. We will relax about member imperfections because we know that they're allowed for in the code clauses. They always have been and they always will be. And for frames, we will check frame stability and we'll calculate alpha. We currently know it as alpha crit. And if necessary, we will do an amplifier. The alternative to that is that we do a second order analysis of the frames. So really no change, but I think that flowchart will cause a lot of confusion when people get to it. If you're a researcher, instead of relaxing and knowing that the imperfections are covered in the resistance formulas, you could model your members with initial imperfections. I don't know why anybody would want to do that unless you are a researcher, but here you can, and here we have some new values. And I just share a twinge of amusement, really, that somebody has spent a lot of time and worked out very precise values, 1/68, not 1/70 or 1/65 or something like that, but 1/68. So somebody somewhere, I think, will be very proud of their work in calculating 1/68. This is classification. So the areas that are highlighted are where classification changes have been made, and these classification changes are always more conservative. So in some cases, you will find that a member, when you classify it to the Generation 2 Eurocodes, is in a higher class. So it might have been in class 2, and now you might find it in class 3. And of course, that's a worse situation, really, in terms of resistance, because as you go from a low class, class 1 to 2 to 3 to 4, then of course the resistance is diminishing. Some of this, again, seems rather like curve fitting. So over on the left, that's where we were currently. Some of it looked rather neat, I would suggest, before, because this denominator just highlighted now. You can see what was happening there when psi is 1. Well, the denominator becomes a nice round 1, value 1, and therefore we're left with 42 epsilon on the numerator. Well, over on the right-hand side, thanks very much. We've now got a quadratic, and it's just becoming a little bit painful. We had 62 epsilon here. Now we've got 60.5, and you wonder whether the changes really are so very significant. I am being a bit cynical here with this graph. These are the classification limits plotted now for when you change from class 1 to class 2. I'm being cynical because at this scale on the right-hand side of the curve, you can't really see any difference. If you enlarge that right-hand side from alpha greater than 0.5, you would see a small difference there. But remember, you're reading across to this value on the left-hand side. So it might now be 18. No, it might be 28. And maybe the value before was, I don't know, 30 or something. You know, so a little bit of change in that sort of area. This is the class 3 limit. And again, well, I'm plotting the entirety there. Psi value on the bottom scale from -1 to +1. And you can see the generation 2, which is dotted, has got a very slightly different curve. And again, it makes you wonder, well, was it worthwhile? Did it make so much difference? Are we so clear about the modeling of our loads? Are we so clear about the modeling of our structure that we really believe the bending moments and the shears and the axials are precisely correct, sufficient that this change makes sense? Sometimes I think we need to remember that we're just modeling the loads. We don't really know what the loads look like. We model them as UDLs or point loads. They're not really like that. And our frame analysis, well, again, that's a model of reality. Rather profound, really, for a Wednesday, but here we go. This is some good news, I suppose, if you're using circular hollow sections or ovals. Not many people are using ovals unless you're at airports like T5, I suppose. But there are some helpful changes to the classification limits. So if you were using circular hollow in bending or compression, and you were using oval in bending and compression, then there would be an advantage for you. Now, this is an introduction to the work which has gone into Annex B with semi-compact sections. This is a moment rotation curve. So moment on the box, no, rubbish. Moment on the vertical axis and rotation on the horizontal axis. And this is how beams behave. Class 1, we would get past the plastic moment of resistance. We get past it because of strain hardening. We can rotate it a long way. Class 2, we equally get past the plastic moment of resistance, but we can't rotate it very far. Class 3, well, we're less than class 2, and therefore we generally limit ourselves to the elastic moment of resistance. But as that class 3 curve shows, we're going to fall somewhere between the elastic moment of resistance and the plastic moment of resistance. And the Eurocode is saying, I'm going to give you a procedure that you can work out that resistance. And we work that out by using a effective plastic modulus, WEP. The generation 2 formula is on the bottom left-hand side. So we start with the plastic modulus and we subtract a proportion, that's beta. We subtract a proportion of the difference. So the difference is the plastic modulus minus the elastic modulus. That's what we've got to play with. And we subtract a proportion. In BS 5950, which has been around since 1985, we started with the elastic modulus and we added, well, some part of the difference. That's the difference between the plastic and the elastic. And this really is the ratio, which on the left-hand side is presented as beta. It's to do with the classification limits and how close you were to the classification limits. So same thing, really. It's been around for a long time in BS 5950, and it's just made it in slightly revised form into generation 2 of the Eurocodes. My good friend Richard Henderson wrote about this back in 2022, so we've been opening up these Eurocodes for a long time now. He identified that to develop the guidance in the generation 2 Eurocodes took 3 years, a whole load of euros, and well, you get 1% difference from had you done it the way which is set out in BS 5950. So I suppose it might have been more cost effective just to take the BS 5950 rules and import them directly into the Eurocode. I'm a little bit sad about this change. This is the table where we identify which buckling curve we use for flexural buckling. So we'd use this for columns. And for the last few years, I've been exhorting people to use S460 for columns. Not only is it stronger, but you get a very healthy improvement in the buckling curve. Well, in generation 2, it remains stronger, of course, because it's S460, but the advantage of the buckling curve is not so pronounced, which is disappointing, really. We were saving money, we were saving carbon, and now in generation 2, it won't be quite as advantageous to select S460. My favorite subject, which is a bit sad to say, is lateral torsional buckling. The lateral torsional buckling rules in the Eurocode are changing. There are, in fact, 3 ways of doing it. There is a very simple case where you just identify the compression flange and treat it as a strut. There is the general case, which the Gen 2 Eurocode says you can use for UB and UC. And there is a special case. And you really would rather hope that the special case gives an improved resistance. You're putting more work in. You would expect it would give an improved resistance. Sadly, that's not always the case. You can find situations, limited, I agree, where in fact the general case gives a better resistance, a higher resistance than the special case. So you can imagine us here at the SCI when we prepare the blue book to generation 2. Not only are we going to have to consider the special case, we're also going to have to consider the general case, because sometimes the general case gives an improved resistance. So here is the general case. It's a very easy selection of buckling curve, curve A or curve B, just based on the H/B ratio for the particular member. And once we've done that, we use the column buckling curve. Notice that, ladies and gentlemen, we use the column buckling curve, but we just substitute into it the lateral torsional buckling terms. So that's dead straightforward, dead easy. When you look at the formulation, you would recognize, I think, the value highlighted in red is the length of the plateau. So if our slenderness is less than the length of the plateau, there is no reduction due to buckling. That's what that value is when it appears in the formula. All very good, but the Eurocode says for lateral torsional buckling, there is no reduction if the slenderness is up to 0.4. That is a nationally determined parameter, but I would expect that the UK would endorse this value of 0.4. So in the graph on the right-hand side, the sort of diagonal line is not in fact a straight line. That's just the start of the curve drawn at a very high scale. And you'll notice the start of the curve intersects with the plateau at 0.2, but nevertheless, there is no buckling. That's the solid blue line until we get to a value of 0.4. So we're going to get some discontinuities, aren't we? Just below 0.4 and just 0.4. That will be interesting, and I think people will have questions about it. So then we move on to the special case, and all I will say about this is it's much more complicated with additional variables. So here is the formulation, and I'm highlighting things in different colors here. The first one is highlighted in blue. The minor axis slenderness now appears in the expressions to calculate lateral torsional buckling. That's a new thing. So when we calculate LTB, we need to work out the flexural slenderness in the minor axis. That's lambda bar Z. So that's an additional complication that we need to deal with. The next thing is the imperfection factor, alpha LT. So here is the table that tells us about alpha LT, and you'll see highlighted on the left-hand side of that red block, you will see that it is a value, but it has a limit. And the value is something to do with the square root of the elastic modulus in the major axis divided by the elastic modulus in the minor axis, which means if you are not governed by the limit, it means that the imperfection factor for your section is unique because it depends on the ratio of the elastic modulus in the major to the elastic modulus in the minor. So no longer a consistent set of standard curves. It will be a unique relationship if you are not affected by the limit. So of our universal beams, just over 60 are impacted by the limit. So they're okay, I suppose. Another 50% will have a unique value of alpha LT. All of our universal columns will have a unique value of alpha LT. And then the FM factor, which you would have seen a couple of slides ago. This is my example of curve fitting. You'll see here we've got ratios to the power of 3 and to the power of 2 and the power of 4. Definitely curve fitting. For a limited shape of bending moment diagrams, I would have loved it if the value of FM was related to C1, because both C1 and FM is associated with the shape of the bending moment diagram. Unfortunately, there is no relationship between the value of FM and C1, which causes us problems when we get to the blue book. If we bring all those things together, what you should be looking on this particular graph is the green line, and you should be reading it against the scale on the right-hand side. Nice beam, 305, 165, 46, lots of those around. Uniform bending moment diagram, so C1 is 1, and down at the bottom here, you can see that the reduction compared to Gen 1 is 14%. So the Gen 2 lateral torsional buckling resistance is 14% lower than Gen 1. Of course, I've picked one where there's a bit more drama. The reduction tends to be between 0 and about 12%, but it can be, in this case, up to 14%. Here is universal columns used in lateral torsional buckling. A very familiar one, 203 UC46. Well, I don't know what sort of length we would use these for lateral torsional buckling, but in this sort of area, we're losing 4 to 5%. So it depends on the member, it depends on the shape of the bending moment diagram, it depends on the buckling length, of course, but you should expect to see that lateral torsional buckling resistances are reducing in Gen 2. Here's a real version. We always like 533-210, so this is 92 kilograms per meter. You can see that the special method gives us currently 265. Well, the Gen 2 method will give us 92%, so we've lost 8%, and that, I guess, would be a typical member. So yeah, we've got problems then when we come to the blue book, because our blue book is presented against values of C1, but there is no relationship between C1 and FM. So the only game in town is to set FM to be 1. Well, that will be very painful for the areas where we do actually know what C1 is and we do actually know what FM is for certain shapes of bending moment diagram. Because in this top block, highlighted now with this hand-drawn circle, we don't know how the value of C1 has been derived. We don't know the shape of the bending moment diagram that has led to that value. So therefore, we have to set FM to be 1. So those 3 rows at the bottom, we do know C1 and we do know FM, and therefore we can use both those factors and we can get the appropriate resistance in the body of the table. So that will, again, I think, be a challenge to people come Gen 2. Axial load and bending, we would have known these as 661 and 662, so no significant change there. The interaction coefficients, they're sort of presented in the same way. Now we've got this fella here, NY, and you think, well, what is NY? Well, strangely, NY is exactly what it always was. So we've made it simpler by, well, just rearranging that and extracting the value of NY. Good news here. It's confirmed that if we only have major axis bending and compression, then we can simplify these expressions. It gives us advice on the coefficients that we can use here. That's good news. It's just practical, because when you look at these coefficients, for example, the one which I've highlighted again in the bottom line there, that's always about 0.98 or 0.97. So really to say it's 1, we're kind of okay. And over here on the left-hand side, that's just the conservative value. So if we take a conservative route, that's what the Eurocode is telling us we can do. Maybe this is good news. This is when we've got torsion involved as well. So we've got axial, major axis moment, minor axis moment, and torsion. That used to be in 1993 Part 6 for cranes, and now that's been imported into 1993 1.1. This is Annex E, and it's telling us about the production statistics. So it's telling us what the mean is, and it's also telling us what various standard deviation values below the mean are. So this is normal sort of statistical stuff. You take the mean, you remove a number of standard deviations below the mean, and you can determine the characteristic value or the design value. And effectively, that's what's been done to calibrate reliability. Okay, and researchers, I think, would be very interested in those statistics. Some things which have gone, Annex A, that's not a sad thing. I've mentioned that before because I don't think we used it in the United Kingdom. The stable lengths next to plastic hinges, this is the third time mentioned that. Sad deletion, but it will be resurrected in an SCI guide, so probably that's okay. Now, another good thing is in the area of brittle fracture. So you will perhaps have been on an SCI course before, and you'll know that brittle fracturing in the Eurocode is really related to fatigue, and the SCI produced a different guide where there was no fatigue. So you could use those values if you were building a building where we wouldn't normally have fatigue as a design consideration. Well, the Eurocode sort of recognizes that because it now has two core tables. Unfortunately, it has tables for execution class 1 and execution class 2, where really that is no fatigue. And then it has a different table for execution class 3 and 4, where really that is fatigue. So it's a bit of a shame, really, that it refers to execution classes when really what it's doing, one includes the effect of fatigue and one excludes the effect of fatigue. And maybe that will be clarified later on, and maybe that will be clarified in the UK National Annex. So we have P419 as an SCI publication, and if you look at the core table for what it describes as execution class 1 and 2, but really it's no fatigue, well, you see the same advantage that you have in P419. Let's take a J2 at -20, the value here 50 millimeters. J2 at -20 without fatigue, well, it's a huge advantage, isn't it? 240 millimeters. So this is good news. We currently have a large national annex to the Gen 1 version of this. I expect that we will have a very large annex to the Gen 2 as well. So other than saying what I expect, I don't know anything of the detail. We wait to see. So no further comments really on that area. 1994, that's composite. I thought I'd better put a word in about that. And 1993, 113, they're sort of associated because lots of people do composite beams with holes in. There are some changes, but hopefully, no, not hopefully, but thankfully, most of it is exactly the same as you would find in the SCI guide, mainly because one of my colleagues, Professor Mark Lawson, he was the convener of the Eurocode working group, as well as the author of the SCI guide. So maybe we would expect that to happen. 1994, really composite, not my area, but there are a few changes. Some of the changes appear to involve a lot more calculations, but they don't sort of have any particular impact. These are a list of the changes around 1993, 113, so beams with web openings. So some additional sorts of things there, but as I say, not much change from the SCI publication. Joints then, give you a few highlights out of joints. Well, the code has been revised in terms of its layout, so lots of components are now found in the annex rather than in the core part of the Eurocode. A bit of drama is in the bearing, the calculation of bearing resistance. So looking at the diagram on the top right-hand side, the formulation of the bearing resistance clauses is no longer interested in E2 and P2. The line of the action of the force I've now drawn on. So E2 would have been the edge distance, and P2, I would have known that as gauge. But those two variables, those two dimensions, no longer appear in the formulas. Now, I don't want you to necessarily appreciate the detail here, but if we look at the formulation of the resistance calculations, I'm interested in the value which I've highlighted now, what it was and what it is, because everything else is the same, the ultimate strength, the diameter, the thickness divided by gamma m2. I'm only interested in the product of those two factors highlighted in the two expressions. Well, Gen 1, the maximum product of those two values could have been 2.5. Gen 2, it's 3.0. So that's telling you that the bearing resistance is, again, potentially rising considerably. And again, I don't particularly need you to look at the values, but compare the 50 to the 81, compare the 90 to the 161. Now, in most cases, it's sort of irrelevant because if you're sharp-eyed, you'll recognize that this is for M20 bolts, and the shear resistance of an M20 bolt is 94 kilonewtons. So yeah, I know probably people would be saying, well, you could have a bolt in double shear and then you would take advantage of that increased bearing resistance. But for many connections, it will not be much help. Here's something which I'm particularly twitchy about, and other people in the United Kingdom are as well. This is the depth of a drilled and tapped, so drilled and threaded hole into material, the depth that you would need to achieve the full tensile resistance of the bolt. Now, I don't like this because a normal bolt is very high strength, typically 1,000 newtons per square millimeter. And here we've got depths of engagement for plate, for example, S355 plate, which has an ultimate strength of 470 newtons per square millimeter. So the ultimate strength is about half, but we still don't seem to need very much depth in plate. So an M20, 8.8, in S355, the factor here, 1.11 times the bolt diameter. So to me, not a very deep threaded hole, but the material is substantially weaker. So there are some tests going on now to try and verify whether this table is correct, and maybe that will be changed in the UK National Annex. Some people use cold formed square hollow sections or rectangular hollow sections, and there is a limitation on the welding around the corners of those sections, which you currently find in 1993-18, and people might rejoice because when you open up 1993-18, the Generation 2 version does not have that requirement in it, and you might think, great, I can weld merrily around the corners of cold formed square and rectangular hollow sections. Sadly not. That requirement has been imported directly into 1993-110, so it still appears, it's just in a different place. Some good news again, which I like. I know that the web panel is often the weak link in a joint, and lots of people use a supplementary web plate, and I'm always a bit questionable about these welds here, welded into the root radius. They're very large and they're painful to do, and access is not straightforward. Well, now the Eurocode says that you can put your supplementary web plates a little way away from the web. So in my personal opinion, that's the web and that's the root radius. It would be great to put the supplementary web plate just here, just stepped back from the root radius. And then there would be sufficient room to get bolts into the flange. So I think that's a good idea, and that's a helpful detail, and I hope people start to use it. There is an annex in 1993-18 which provides information on rotational ductility, if you like. Where do connections get their rotation from, and how do you measure it, and is there sufficient? The UK have been producing the green books, which have been used satisfactorily for decades, and we will decline, I think, to use the annex in the Eurocode, and we will, as we do in Gen 1, refer to the green books. So, here's a bit of plus and minus. I know this has been a whistle-stop tour, ladies and gentlemen. It was never intended to be anything in great detail. It was always intended to just give you a flavour of what's coming your way, and probably, if I'm being honest, make you a twitch nervous, because I think the changes are considerable, and many of the things which you use, your resources, your software, etc., etc., are going to need to change. And if you're a consultant working in multi-materials, of course, you have a much larger problem than just steel. But here's my personal view. Is it an advantage that we've got increased precision? Well, I've got a question about that. I think the fact that there are now 2 tables in the subgrade part, so 1993-110, is a good thing. We wait with anticipation to see what changes the UK National Annex will make. We've now got a plastic modulus for Class 3 sections. Well, that won't apply to many sections, so it's not so much of an advantage. And of course, BS 5950 had it for, what, 40 years or more? Guidance on web openings is good. That wasn't part of the Eurocode before. It was just in an SCI publication, so that's good. And I genuinely think that guidance on FE is starting to become very common. That's a good thing. On the right-hand side, these are my concerns. In many areas, we'll be working harder. Well, maybe we won't if we're using software, but if we're doing manual calculations, we will. And the advantage, I think, is, well, minimal. In my particularly interesting area of lateral torsional buckling, lots more effort, but in fact, the opposite is true, a reduced resistance. And on the 1st of April 2028, that's going to cause some concern. I think things that you designed yesterday, if you redesigned them the following day, their resistance has apparently dropped, and that could drop reasonably significantly. Right, 2 more slides to finish off, and they're important, ladies and gentlemen, so please hang on and then I'll have a look at the questions. What's going to happen as far as the SCI is concerned is you can imagine we will start to be preparing and rolling out detailed courses. So there's an awful lot of topics which I've covered in this 1 hour. You could imagine that there will be courses on various of those individual topics. We are also we're in the early days of updating some of our guides. More of that in 2 slides' time. Okay, so that's generally what will happen, and I suggest that you keep your eye on the website and you'll start to see more and more Gen 2 stuff coming out of the SCI. In the short term, these are the things that are happening. We've got some courses on light steel framing and disproportionate claps in April and May, respectively. The next webinar is, in fact, me again. Sorry about that, ladies and gentlemen. On the 22nd of April, that will be for members only. And that's to do with single-story steel frames in boundary conditions. So you'll probably know that things are changing there. And I'll go through the background and talk about some of the implications. The next free-for-all webinar is to do with 1991-11 wind loads and some software which we've developed, Cypher or Zephyr, I think you say that, and that's on the 29th of April. Now, before I look at the questions, 1 final slide. Years ago, we used to have British Steel, who became Chorus, and British Steel were a massive supporter of the steel industry, and they funded lots and lots of guides, and they funded an awful lot of Eurocode guides and Eurocode work, and we, the SCI and others and the industry, very grateful for that support. Well, they no longer exist in that sort of form. So there is no longer that sort of external funding for the very necessary resources which are absolutely required. So there is an opportunity, ladies and gentlemen. There is an opportunity to help with that effort. So if your company has a marketing budget, for example, and would like to find themselves perhaps on the covers of some of our publications or inside some of our publications, to recognize that you have contributed to the needs of the industry, well, perhaps you would think about perhaps helping out with that effort, because it is a really considerable effort. If you are interested at all, well, then there's the email at the bottom there. And we're trying to see what interest there might be. So we've put an end date to register your interest, and that will be the 17th of April. With so many changes, does this mean things were wrong until now? It means that you would have a reduced level of reliability. That would be a different way to say it. Okay, somebody's saying, yes, everyone will have to go back through the last 20 years of work and redesign everything. We don't do that, do we? We don't go back, but we do adopt these things going forward. With the changes to the snow loads, is the rule stating roofs need only be designed for live or wind hour snow retained? That was a very nice rule for buildings found in 1991-11. And you catch me on the hop. I don't know. A very good question, and I'll have to find out the answer to that one. Does the industry and academia really understand the changes and challenge that is coming and the clock is ticking? I don't think they do. Whoever said this, I don't think they do. Oh, and they're saying the changes are potentially huge. Well, I agree with you. And that's been the theme of this webinar today. They are potentially huge. Yeah, so then the comment is going on to range a whole list of things which need to be changed. Absolutely, it does. Somebody's saying, snow not counted as an accidental in the current codes. Well, no, I think this question is to do with removing snow from one roof slope. That's a persistent case even in the current code. So I think if that was your comment, you're absolutely correct. What do I think about calculating the effective buckling length for U-frames? Well, it's something I've not looked at, but I'm sure it's good stuff and been proved by lots of research. The aim of consistency of classification limits is the aim of the change of class limits is to restore consistency between EN 1991 and EN 1993-15. Okay, but I think they're actually pretty consistent, because when I looked at it, I calculated a classification limit of 13.9, I think, in 1993-11, and it was 14 if I'd have sorry, 1993-15, the figure was 13.9, and in 1993-11, it'd been rounded up to 14. So maybe I missed it, but I thought they were consistent anyway. Oh, what's the justification to change the section classification and LTB, making it worse effectively? It will affect the carbon footprint. Yes, it will. But that means that your level of reliability has been restored. More effort, more complication, more costs. Yeah, I think so. Yeah. Anything related to vertical and horizontal deflection, I think the UK National Annex is going to retain exactly what we've got now. I see some friends have listened in. So to you, you know who you are. Good to see you in the audience, and thank you for your very kind comments. That's always very helpful. So I shall turn my camera off. See you later.